Welcome to This Explainer. Today, we're exploring a seriously fascinating intersection. We're going to look at how ancient astronomical science, local atmospheric realities, and that little mobile app right there in your pocket all completely intertwine. We honestly take our digital notifications for granted most of the time, right? But behind every single alert is this incredibly beautiful, complex dance between the Earth and the Sun.
So let me pose a pretty relatable modern mystery to you. Imagine you and your neighbor are hanging out in the exact same city, maybe even sitting in the exact same room. Out of nowhere, your smartphone buzzes for prayer. But their phone, completely silent, and it only decides to buzz a few minutes or maybe even an hour later. It leaves you sitting there wondering if one of you accidentally switched time zones. You're in the same location, literally looking at the same sky. So what's actually causing the difference?
Okay, let's dive into this. Let's take a classic example. App A tells you the afternoon prayer, Asr, is at 3:15 p.m., while App B insists, nope, it's at 4 p.m. Well, I want to assure you right off the bat, these discrepancies are absolutely not bugs. Nobody's code is broken here. Instead, what it really comes down to is a mix of specific astronomical parameters and scholarly interpretations that your app is quietly crunching behind the scenes. To solve this little mystery, here is our roadmap for the explainer. We're going to cover 1. The prayer time mystery, 2. The code breakdown, 3. The Asr shadow divide, 4. Twilight and sun angles, and finally, 5. The methods matrix. All right, let's get right into it.
Section 1. The prayer time mystery.
The absolute most crucial thing to understand right out of the gate is that every single reliable prayer app out there is running on the exact same mathematical backbone. They are all using perfectly established astronomical physics to predict exactly where the sun is. Let's kick off our code montage with the formula for solar declination. Basically, this is the angle between the sun's rays and the Earth's equatorial plane, which, naturally shifts throughout the year because of the Earth's tilt. It's the absolute foundation for figuring out where the sun is on any given day.
Let's see how this actually builds into our daily schedule, starting with the absolute easiest prayer to calculate, which is the midday prayer, Dhuhr. Now, Dhuhr happens at exact solar noon. That's when the sun crosses your local meridian and hits its absolute highest peak in the sky. Apps calculate this exact zenith, they factor in your time zone, adjust for the Earth's elliptical orbit using this really cool concept called the equation of time, and then they simply add a 1-minute safety margin just to make sure the sun has actually started its decline.
As the afternoon progresses, the algorithms really kick into high gear. They are tracking the sun's exact altitude, literally minute by minute, based entirely on your precise latitude. Honestly, it's pretty incredible when you stop to think about it. Our phones are just seamlessly performing this massively complex real-time tracking all day long without breaking a sweat. Now, as the sun drops, shadows start to grow, and that brings us to the afternoon prayer, Asr. Here is the formula used for the standard Asr calculation. Just mentally bookmark the shape of this equation for a second. Okay, now let's immediately contrast it with this Hanafi formula. If you look really closely at the very end of the equation, you're going to see a tiny, tiny change. It's a +2 instead of a +1. And believe it or not, this seemingly small mathematical shift is our very first major reason for why those app discrepancies happen.
Section 2. The Asr shadow divide.
Now, what's really interesting about this is that unlike the other prayers, which are calculated strictly by sun angles, the unique rule for Asr relies entirely on measuring shadow lengths. The traditional rule is to measure an object's shadow at solar noon, which is when it's shortest, and then just wait for it to lengthen. That whole disagreement we just saw, it stems simply from the multiplier applied to that noon shadow.
Let's break that down. The standard school, so we're talking the Shafi'i, Maliki, and Hanbali interpretations, waits until the shadow equals the length of the object itself plus 1 time the noon shadow. That 1/x multiplier, that produces an earlier Asr. On the flip side, the Hanafi school waits until the shadow equals the length of the object plus 2 times the noon shadow. This 2x multiplier means you literally have to wait for the sun to get much, much lower in the sky, which can easily push the prayer time 30 to 60 minutes later in the day. So yeah, if your app is set to Hanafi and your neighbor's is set to standard, you are definitely getting notifications up to an hour apart.
Section 3. Twilight and sun angles.
As our narrative moves into the evening, things get, well, incredibly atmospheric. The sunset prayer, Maghrib, actually accounts for atmospheric refraction. Basically, the Earth's atmosphere physically bends light, meaning apps wait until the sun is mathematically 0.833 degrees below the horizon just to be absolutely sure it has truly vanished from sight. But the real complexity? That happens deep in the night. You see, the night prayers, Fajr and Isha, aren't based on a fixed time on the clock. They're actually triggered when the sun dips a very specific number of degrees below the horizon.
For example, lots of calculation methods trigger Fajr when the sun hits negative 18 degrees, meaning 18 degrees below the eastern horizon. And I really want to emphasize this deep angle here. A larger number means the sun has way further to travel to reach that point. So an 18-degree angle means an earlier Fajr because you're catching the very first, faintest hint of true dawn, what is known as subsadiq. But a smaller angle, say 15 degrees, means the sun is closer to the horizon, which actually results in a later Fajr time.
Section 4. The Methods Matrix. So, who actually decides which angle to use? Well, app developers rely on this massive master table of 22 recognized calculation methods worldwide. Various regional bodies choose these rules based heavily on their specific local climates. Like in temperate Europe or North America, the standard methods work absolutely perfectly. But over in Saudi Arabia, the al-Qura method actually completely bypasses the angle formula for the night prayer. Because of the lingering desert twilight, they instead use a fixed 90-minute offset right after sunset. It's a really practical solution.
And this brilliantly illustrates just how localized things have to get, especially when comparing equatorial regions to, say, the Mediterranean. Take Indonesia's Kemenag method. They use a really deep 20-degree angle for Fajr. Turkey, on the other hand, goes with an 18-degree Fajr, defaults to the Hanafi shadow multiplier for the afternoon, and then they add this really smart custom 7-minute safety buffer to sunset just to account for local topography and fiqh interpretations. It's literally a case of different climates and different geography needing different math parameters.
But things get even wilder up north. Just check out the UOIF method for France. When you get up to those high latitudes, especially in the dead of summer, the sun barely even dips below the horizon. Like, it might never actually reach 18 degrees down. So France's method handles this by offering a really clever hybrid model. They use an 18-degree angle during normal months, but then they shift to a 90-minute offset for the twilight prayers during those extreme summer weeks. Otherwise, the math would just entirely fail. It really is kind of incredible when you step back and think about it. The next time you and your neighbor hear your phones buzz at entirely different times, you're going to know exactly why. It's definitely not a glitch. It's the result of this elegant, centuries-old astronomical science directly interacting with local geographical realities, all being crunched in real time by incredible modern algorithms right in your pocket. So next time your phone alerts you, take a quick moment to look out the window, look at the shadows, look at the twilight, and ask yourself, do you know exactly where the sun is? I hope this explainer has shed some light on the brilliant math humming quietly behind your daily routine. Thanks so much for joining me.